Look closely at this patch of deep space. It appears entirely empty, but hiding right in the center of this darkness is an object so dense it physically warps the surrounding starlight. Imagine taking the mass of 20 suns, billions of trillions of tons of burning plasma, and crushing all of it into a sphere no wider than a small city. This chart shows how that density creates a gravitational well so steep that even light, traveling at a universal speed limit of 186,000 miles per second, cannot climb out of it. The point of no return is the event horizon, the threshold where the light beam finally vanishes and space begins to pull everything inward. Because we rely on catching light to see the universe, an object that traps every photon and reflects nothing back remains entirely invisible. To understand how we track a phantom in the dark, we first have to witness the catastrophic events that create it. Our story starts with giant stars, specifically the behemoths holding 10 to 25 times the mass of our own sun. This diagram illustrates how a massive star lives in a state of peril. Its own weight creates a relentless gravitational force, constantly trying to crush the star inward. It survives because nuclear fusion in the core generates an explosive outward pressure. These two forces match each other, keeping the star in a delicate balance for millions of years. This engine works by smashing lighter elements together to create heavier and heavier elements. Over time, the core builds up thick, dense layers of these newly forged materials. A star is essentially a ticking clock. It only survives as long as it has fuel to push back against its own weight. That clock finally stops the moment the star's core begins to fuse iron. Iron acts as a fatal drain on the star. Fusing it absorbs energy rather than releasing it, which instantly kills the core's outward explosive push. Without that resistance, gravity wins the war. Trillions of tons of stellar material crash inward at a fraction of the speed of light, crushing the core down into a microscopic point. Sometimes this implosion triggers a shock wave that blasts the outer layers into space, a supernova. Other times, the star experiences a complete structural failure, quietly collapsing into the void. This collapse punches a permanent hole in the fabric of space-time. A stellar mass black hole is the gravitational ghost of that dead star, a puncture in space that continues to exert the pull of a sun without reflecting a single ray of light. If a dead star has erased itself from the visible universe, astronomers must look for the secondary effects it inflicts on its surroundings. They look for the cosmic equivalent of footprints in the snow. Astronomers often find a visible star whipping around a center of total darkness. The invisible partner's gravity siphons gas off its neighbor, creating a massive glowing whirlpool. Inside, friction heats this material to millions of degrees, screaming in X-rays before crossing the event horizon. Space telescopes like Hubble identify these specific X-ray signatures to confirm a black hole's presence. As long as a black hole actively feeds, its violent appetite gives away its hiding spot. But the narrative shifts when we consider a stellar mass black hole lies totally isolated. With no neighboring stars to tear apart, there's no glowing disk to act as a beacon. Without matter to light up the edges of the event horizon, the object is erased from the visible spectrum, which leaves us with a chilling possibility. We currently have no way to know if an invisible, dead star is drifting silently toward our solar system right now. We live in a universe defined by extremes, but nothing pushes the limits of reality quite like places where time stops and light dies. This creates an immediate problem for astrophysicists. Telescopes are built to capture electromagnetic radiation, but if an object does not emit or reflect light, it provides no data for a lens to capture. Because of this constraint, humanity is blind to the most dense, powerful engines in the cosmos. Finding black holes requires us to stop looking for the objects themselves and start looking for the marks they leave on space. To understand those marks, we have to clear up a common misconception. Black holes do not function like cosmic vacuum cleaners, actively searching for matter to pull in. If you replaced our sun with a black hole of the exact same mass, the gravitational pull would remain identical. The solar system gets much colder, but the planets stay in their current orbits. Gravity depends on mass, not the object's size. They only interact violently when matter crosses a specific, close threshold. It's that localized destruction that gives us the clues we need to find them. Astronomers hunt for black holes by searching for the wreckage of matter that wanders too close to that invisible boundary. As gas and dust are pulled inward, they form a swirling accretion disk. This material is squeezed and compressed until it superheats, blasting out X-rays that telescopes can detect from millions of light-years away. On a larger scale, we can track supermassive black holes by observing how their gravity dictates the movement of nearby stars. At the center of our own Milky Way, astronomers tracked stars moving at thousands of miles per second, whipping around an empty point in space. These high-speed orbits provided evidence that these stars are physically tethered to a massive ghost, a black hole 4 million times the mass of the Sun. For decades, these observations remained circumstantial. We could see the effects of black holes, but the objects themselves remained theoretical. In 2019, the Event Horizon Telescope collaboration synchronized global observatories to create a virtual telescope the size of our entire planet. They captured a direct image of a supermassive black hole shadow in the galaxy M87, located 55 million light-years away. The glowing halo of burning gas in the image outlines the event horizon, the point of no return where light is trapped by gravity. For the first time, we had transitioned from deducing the presence of these objects to directly observing their physical borders. But shadows only exist where there is light. To find isolated black holes wandering the dark void, we needed a different approach. We had to develop a way to detect gravity itself, rather than the light surrounding it. In 2015, two black holes a billion light-years away slammed together at nearly half the speed of light. The collision produced no light, but it released a burst of energy 50 times more powerful than the entire visible universe. That energy rippled through space-time for 1 billion years, until detected by the massive vacuum tubes at LIGO as a tiny, perfect chirp. This signal proved that space can ring like a bell, allowing us to literally hear the movement of dark matter through the void. A century ago, Albert Einstein struggled to accept that black holes could be real. Today, we have mapped their shadows and recorded the echoes of their collisions. These observations have revealed that black holes are more than just engines of destruction. They are central to how galaxies form. Evidence shows that most large galaxies, including our own, are anchored by a supermassive black hole. In some cases, these black holes appear to have formed before the stars that now surround them. By exerting gravitational control over gas and stars, these invisible titans act as the anchors for the large-scale structures of our universe. Our understanding of the invisible has advanced further than Einstein could have imagined. We can now track their movements, photograph their borders, and hear their cosmic echoes. Yet, the event horizon remains a physical boundary where information stops. It is the absolute limit of what light and mathematics can currently reveal. If black holes hold the secrets to how our universe began, they also hold the secrets of what it will eventually become.